All right, y'all, we're going to be finishing up chapter 10 here. So we're still sticking with confidence intervals and as a way to estimate our means. And today we're going to focus on two things mainly, the difference in mean distributions, but also we're going to go back to our work that we did in the experiment chapter. And we're going to talk about, like, if you remember matched pairs designs and how to pair up our data to find the difference and create a new distribution from that. I know that sounds like the same thing, but they are very different things. So, again, a comforting moment here. You're going to see a lot of familiar friends, like, for instance, the condition. So we're going to start with, remember, this time we have a difference of two distributions. So we're going to start with these two samples that are separate, and we got to make sure that each of the samples are independent from one another and that you're randomly sampling for both of the groups. Um, and they're specifically saying in a randomized experiment here. So 10% condition must be checked for both of the samples. Assuming that you're doing this without replacement. We have seen examples in the past where replacement was not an issue because of the nature of the setup, but if you do have to check the 10% condition, it's what it always is. And then remember, we're working with means today, so we're not doing large counts condition, we are doing the large sample or the normal check to see if we can use the T procedures. So each sample, if 30 or larger, would make this good to go to use the T procedure. However, if we are not sure about the original shape of the distributions and our sample size is less than 30, then what we have to do is look at a set of sample data for each and then look at the distributions in some format, box plot, dot plot, something, and make sure that there's no extreme outliers or really strong skewness. A little bit's okay, but not a lot. So we have a great example here. We got a college student who's trying to compare the cost of a one-bedroom and a two-bedroom apartment. So she collects some data, what a studious student, on monthly rent measured in dollars for a random sample of 10 apartments of each type. So 10 one-bedrooms and 10 two-bedrooms. So mu sub 1, let that represent the true mean monthly rent for all one-bedroom apartments in her near her campus. And mu sub 2 would be the true monthly mean for rent of all two-bedroom apartments near campus. So first things first, check the conditions. So these were randomly selected and independent samples. You cannot be both a one-bedroom and a two-bedroom apartment. So that checks out. The 10% condition, let's assume that 10 is less than 10% of all of the one-bedroom apartments near campus. That seems reasonable, and same thing for the two-bedroom. Now, the sample sizes were well, not very small, but they were too small. I already forgot what they were. Was it 10, right? Okay, so 10 is not greater than 30 or equal to 30. So what we have to do then is look at the distribution for each of the samples. So one bedroom versus two bedroom. And, you could make some arguments that there may be some outliers, but nothing super extreme, and then no extreme skewness happening. So we're going to say that the large sample slash normal check is good to go. So same formula that we always use for confidence intervals, but now we have the statistic being the difference in the two sample means. So you have to signify order somewhere in your problem. So the formula just always says x bar sub 1 minus x bar sub 2. Plus and minus a critical value, which remember our work from 10.1 is going to be a t star value. And then the standard deviation of the statistic, which we will use something weird, because remember, if we're trying to figure out what's going on with the overall population, probably a pretty good bet that we have no idea what sigma is. So what we're going to have to do is use standard deviation of the samples. So we're going to do the same formula that we've used before, but now we're going to swap out sigma for standard deviation of the sample, S, and we're going to find the variances, add them together, and then square root them, like we always do for the difference of two distributions. Ugh, don't you just love it in stats when you just predictable, right? I probably could have not shown you that formula and you would have come up with it on your own. Oh, but that's weird. They put p hat here. I think that was a typo. Oh, they fixed it on the next slide. Okay, so I need to fix that typo, but I think on your guys' slides that I'm giving you, you're going to see x bar, not p hat. My bad. Anywho, that was called the standard error that we're going to be using. And again, remember the standard error is a part of the formula sheet. You got to turn to the second page for that one. It does get a little confusing, who are you looking at? So if you really focus on like the similarities between all the problems. Then you kind of get a feel for what you should be looking for. So, assuming all the conditions are met, you can find a C% confidence interval for the difference of the true means by using this glorious formula, which again is not explicitly on the formula sheet, but you can Frankenstein it together. We're going to have to worry about degrees of freedom again in this lesson. So because we have two samples that we're pulling from, it's not obvious what the degrees of freedom would be because oftentimes the samples are different sizes. So you have two options. You can use the technology option, which you know I'm going to be a fan of, and it'll just give you the degrees of freedom as part of the interval. Yay. Or option two is you take whoever the smaller sample size is, and then subtract 1, and that'll be your degrees of freedom for this problem. Now, that is a very conservative way to do the problem, and what you'll find is if you use technology, you'll get a more accurate and reasonable answer. The conservative method will give you a much larger confidence interval, and that's just the name of the game when you don't have technology to rely on. I know there's a lot of complaints about these kids and this technology these days. Well, technology has made a lot of amazing improvements for our lives, and one of them is better stats, not just easier stats, but better stats. All right, so here we have a problem about a preserve in Georgia. The Wade Tract Preserve is an old growth forest of longleaf pines that has survived in a relatively undisturbed state for hundreds of years. One question of interest to the foresters who study this area is how do the size of longleaf pine trees in northern and southern halves of the forest compare? So to find out, they took some random samples, 30 trees from the northern half and then 30 trees from the southern half, and they measured the diameter at breast height, abbreviated DBH, in centimeters. Here are the summary statistics. All right, they put them in box plots. That was nice. Oh man, this is going to be a blast from the past coming up here. They're going to ask you to compare the distributions. So way back in the day, remember we had a silly acronym, but like I kept saying something goofy like SOCOV, shape, outliers, variability, and center. Those are the things that we have to mention when we compare two distributions from back in the day, back first semester. So the shape, and you want to be specific and about context about which distribution you're talking about. The distribution of DBH in the northern sample appears to be skewed to the right. Okay, I agree with that. Their tail is longer on the right, while the distribution in the southern sample appears to be skewed to the left. And again, I think they're both slightly skewed, but there is a definite, mention of skew. I don't see any outliers. We didn't do the 1.5 times the IQR test or anything goofy like that. I was kind of hoping, like, if someone was nice to me, they would put the modified box plots on with the stars when there's outliers. So we'll just go with no outliers. However, if I was nervous, if this was a test, I might go through and like do the 1.5 times the IQR thing. I know it's annoying. It takes forever. Not today, though. All right, the center, you can use a couple different things for center, mean or median, technically in a box plot. But they went ahead and gave you the statistics. So the mean of the southern tree group, let's see, where are we at here? That's 34.5-ish. And then the mean of the northern group was 23.7. So it appears that the southern half of the forest, as far as the center goes, has larger diameters at that height of the tree. So the mean and the median for the southern sample are actually larger. So if you look at the medians, remember the middle of the box plot, the median is also significant. Well, I shouldn't say significantly. That's a naughty word to use right now. It is higher than the northern forest median. Variability. Well, you could talk about a few different things. You could talk about the range itself, or you could talk about the interquartile range, or you could look at the standard deviations. So the standard deviation, that's a numerical thing to look at. I like that. It's larger in the northern group. And also, if you just look at the overall range, it's larger in the northern group. That kind of goes hand in hand, so that makes sense. And if you look at the length of the box, it's larger in the northern group. So all of the measures of variability that we use are larger in the northern part of the forest. All right, that was a blast from the past, wasn't it? Now the new stuff. We're going to construct and interpret a 90% confidence interval for the difference in the mean DBH of longleaf pines in the northern and southern halves. So we are going to have to decide what order we want to subtract them in, and it's stated here in our state plan, a part of the plan. So it says 90% confidence interval for mu sub 1 minus mu sub 2, where they're going to say mu sub 1 is the southern group. So it's the true mean for all trees in the southern half of the forest, the mean DBH. And mu sub 2 is the true mean DBH of all trees in the northern half of the forest. So again, remember for mean, you want to make sure that your context is appropriate so that it's the true mean. So we're talking about the parameter mean this time for all of the things in the population that you were discussing. Now, again, they were only talking about trees in this particular forest, northern half versus southern half. So that's your population. All right, plan time. We are looking at a 2 sample t interval for mu sub 1 minus mu sub 2. So you got to check your conditions on the plan step. These are independent samples because these forests are mutually exclusive. You're either northern or southern, not both. They are random samples. They stated that in the earlier part of the problem. And they did sample 30 trees from each forest, I believe. So 30, oh, phone's going off. It's the hub, so I'm gonna have to pause. Sorry, I got click happy trying to get out of that screen. Hold on. Before my husband interrupted this. Okay, we're in the middle of checking our conditions, I believe. So 10% condition, 30, I mean, it's very reasonable to say that's less than 10% of all the trees in the northern half of the forest. And same thing for the southern half. And then 30 is, someone asked me this in class though. They were like, can I just say 30 is equal to 30? And I said, probably, but the book always does this. 30 is greater than or equal to 30, which is true. It's not wrong. So therefore, you are hitting the large sample condition, that we need to hit for looking for that normality. So check, check, check. We're good. All right, so now we're on the do stage. And I think there's slides coming up to show you the technology stage, but I'm sure you've put this together by now. When we use technology, we've been going to the stat test menu, and because you have a 2 sample t interval, you're going to pull up 2 sample t interval. But what I will point out to you is, and there's going to be a slide coming up, I bet, warning you about this. Your teacher is going to suggest that you go ahead and use the technology on these problems because the formula is real clunky and it's hard to use and it's really easy to screw up. The other thing that would be benefit if you use technology here, you don't have to worry about degrees of freedom. Now, this problem wasn't like awful to use the table because they were both 30. So it's like, oh, well, degrees of freedom would be 29. But the true degrees of freedom for this distribution, this difference in the distribution of the differences, difference of the distributions, sorry, is actually 55.728, which is not what you're going to get from table B. So this is going to be a more accurate this will be a more accurate confidence interval based on how it's calculated. Remember, the table is just like a generalization and approximation for when, like, you know, you need a good enough answer, or frankly, back in the day when we didn't have calculators to do this. I will tell you, though, if you're using technology, you still need to state out all of the pieces that you're entering into the calculator. It's not that hard. You just copy what you're typing in. And the menu on the calculator will prompt you just like this one does. So X1, S1, N1, I should say X bar 1, and so forth for the second sample. Now, if you're a tried and true table B'er and you want to do this by hand, your degrees of freedom would be 29. So you'd be going over to table B and you'd be finding an appropriate T star value, which according to the table is 1.699. And you're going to come up with a slightly different confidence interval. So they got 3.8 to 7.8-ish, and then over here it's 3.9 to 7.7. So you see, even with like a very different degrees of freedom calculation, it's not that far off, okay? So that's why we always say in stats, like, pick a method, go with it, good enough, as long as you can explain it on a free response question. But I will tell you, doing this by hand is kind of atrocious. And I know myself, I screwed up. So you won't be seeing me do this one by hand. I might set it up and then like kind of use the calculator. Now, the warning on that is, as you can see, the calculator's answer versus doing it by hand is going to give you a slightly different interval. So if I was testing, full disclosure, guys, I might try doing it by hand and I'm going to follow it through all the way to the end. I'm still going to check it on the calculator because I'm very paranoid. Now, if I was running out of time or I have done so many practice tests that I know on a free response question this is going to take me too long, then I might decide this is the way I want to do this question. So we know from free response land that I'm allowed to use the calculator as long as the problem calls for it as an allotment, and I explain what I'm doing. That's the key. And then the conclude step. So depending on which interval you went with, you're going to say you are 90% confident that the interval from whatever centimeters captures the true difference in the mean DBH of all southern trees and the true mean DBH of all the northern trees. So again, I like when they're a little, like I know we defined mu sub 1 and mu sub 2 earlier in the problem, but I kind of would prefer it done in words here, the true difference in, you know, southern minus northern. I don't know. I'm just thinking like if I was a reader, well, obviously I read your guys' tests all the time, but like what would I want to see? So I don't know. Think about an easy way to write those. You don't necessarily have to follow the exact formula they have there. Okay, so here's the calculator. So this is in the stat test menu, and I think it's choice 0, but don't quote me on that. You're going to choose two sample t interval because you have two samples. It's a t test, or a t interval. And you have an option of stats or data. So for this question, I think we actually did have data. So you could have put data in list 1 and list 2 and then said that, but otherwise, if you've already calculated the stats, you can just do stats. So they entered sample 1 mean, sample 1 standard deviation, and then your sample size for number 1, and then same thing for 2. They set up the confidence level, and then when it says pooled for your data, you want to say no right now. Pooled means you're going to combine them together, which we're not doing right now. So it's going to pop out this baby. It's going to give you the interval. It's going to give you the degrees of freedom, which you would have to write down on a free response question as your solution. You don't have to write down the X bar, S, and N because you already gave that earlier in the problem because that was part of your do step. If you put your data into the lists, this is from the apartment example, it would ask you what lists your data is in. So most humans put, data in list 1, list 2. You just got to make sure you know what's where. And then if you have a frequency list that is multiplying anything, then make sure you indicate that. Otherwise, if you're going to keep frequency as a 1, that means it's not going to multiply your list by anything. And same thing happens. You're going to end up with, and this is a different problem than the previous slide, but you're going to end up with a confidence interval, a degree of freedom, and then it's going to have all the statistics that you're going to want to jot down on your do step. When in doubt, write it out. That's my theory on the calculator. So be very explicit and write everything that you're doing on your calculator, and I guess too much information is probably for the better. So the formula for two sample t interval for mu sub 1 minus mu sub 2 often leads to calculation errors by students and your teacher. So the technology interval is actually a better one. It's a narrower one as opposed to the one you would use using table B with the conservative method of going degrees of freedom minus 1 for the lower guy. So as a result, your teacher may and will recommend that you go ahead and use the calculator's two sample t interval. Just make sure that you name the procedure in the in the plan step, and then you write everything out in the do step. So including the interval plus the degrees of freedom that it gives you. Don't confuse your reader by like halfway doing it by hand and halfway doing it on the calculator and writing both of them out. I think they're going to get ornery if you do that. All right, this is a good problem for you to try on your own. Please pause the video and check these out. So we have Ms. Wilcox's class is performing an experiment to investigate whether drinking, I remember this experiment, caffeinated beverages would increase the pulse rate. So 20 students in the class volunteered to experiment here. All of the students measured their initial pulse rate. And then Mr. Wilcox, randomly assigned the students into two groups of 10. So there's the random assignment. Each student in the first group drank 12 ounces of cola with caffeine, and each student in the second group drank 12 ounces of caffeine-free cola. All students then measured their pulse rates again, And here's our data that displays the change in pulse rate for the students in both groups. So we have our two groups separated, the data, and they're going to want us to construct and interpret a 95% confidence interval for the difference in true mean change in pulse rate for subjects like these, because remember, they were volunteers, who drink caffeine versus who drink no caffeine. So answers coming your way. You got to go through the whole gamut here, guys. You got to state we're doing a 95% confidence interval for mu sub 1 minus mu sub 2, where mu sub 1 is, and this is where you choose what it is, but they set it up where it's the true mean change in pulse rate for students like these after drinking 12 ounces of cola with caffeine. And mu sub 2 is the true mean change in pulse rate for students like these after drinking 12 ounces of non-caffeine cola. So if you already worked ahead and set those up differently, that's okay. You just got to remember that that's the way you set it up. So now we're going to plan it out. We're going to do a 2-sample T interval for mu sub 1 minus mu sub 2. They were random assignments to who's going to drink what. The groups are independent, obviously, because they wouldn't be drinking both of them. And the sample is small. However, if you check out the dot plots of those samples, the sample data, there's nothing extreme happening. There's no extreme skew and there's no extreme outliers. So we're good to go. So now it's the do step. So if you are on technology, you still need to state all this good stuff, which is something you would have typed in the calculator in the paste menu. So it's not like any extra work for you. You just got to write it out. And you're going to use a 2-sample T interval. And then it's going to give you the interval. And after it's going to give you the degrees of freedom that it calculated based on this information. If you're old school and you do this by hand, your degrees of freedom is going to be a 9 because your sample sizes were both 10, so one less than that, which gives you a critical value of 2.262. And then you got to throw all that information into that horrendous formula, even though your teacher told you not to do it. But you know what? Some of you just like formulas. And you get a little different interval. I mean, our interval, yeah, negative 0.13 to 3.7. And then the old school one is negative 1.49 to 3.89. So you'll notice the technology gave you a smaller interval, as promised. All right, so now the conclusion. We are 99% confident that the interval from, and then choose whichever interval you wanted to use, beats per minute captures the true difference, the difference in the true mean change in pulse rate for all students like these after drinking 12 ounces of cola versus 12 ounces of non-caffeine cola. Okay. Was there a second question? Probably. Yep. So what does the interval in question 1 suggest about whether caffeine increases the average pulse rate of subjects like these? Justify your answer. So if you look at that interval, which is here, 0 is included in the interval. Okay. So because of that, 0 is a plausible value, meaning it would be a plausible thing to happen to say there's no change in pulse rate. So we don't have convincing evidence that drinking the caffeine will change the pulse rate. I feel like they said something else in here. Yeah, so it does not suggest that it increases the pulse rate. There we go. In fact, there's plausible values that suggest it decreases the pulse rate. So that's interesting. Okay, so that's probably day 1 of this lesson. And then now we got to go way back in the brain and look at, basically it's a matched pairs design, if you can remember that from chapter 4. So a researcher studied a random sample of identical twins who had been separated and then adopted at birth. So in each of these cases, one twin, they called them twin A, was adopted by a high-income family, and then the second twin was adopted by a low-income family. So both twins were given an IQ test later on as adults. So this was not like something they did to these children, by the way. This was just how it worked out. They researched and found sets of twins where this situation naturally just happened. I know the first time I read this, I thought, oh, this is icky. But then I reread it and realized, okay, maybe not. So what we have here is we have twin A and B, and we're going to end up kind of matching them in a minute. So at first, we're going to look at these distributions independently. So we got twin A, there's their distribution as a dot plot for IQ score. Same thing for twin B. And at first glance, you're looking going, it doesn't really seem to be any difference. I mean, Slightly higher on the twin A distribution, but overall, like it's kind of right there. So maybe there's no difference, high income versus low income. But what this study fails to think about, oh, and there's the actual averages, 109, 103 something. So really not too far off for the average. And variability is pretty similar. However, they kind of forgot that these twins had something to do with each other from birth, right? These were twins. So the fact that twin set number one, went to two different homes, we have to kind of bring that data back together at the end of our analysis and say, okay, how did that difference in environment affect that pair of twins? So we have paired data that we forgot to think about in our analysis. So since we have paired data, um, we're going to have to think about how that changes things. So I know this is going to look at first like, oh my gosh, this is the same thing we just did, but it's not. In the previous part of the lesson, we had two separate distributions where we ended up subtracting the distributions. Here, what we're going to do is we're going to create a new distribution that represents the difference in each of our matched pairs. So we're going to look at pair number one, and we're going to subtract their IQs because remember, these are genetically siblings. And then we're going to compare the difference in twin A minus B for IQ score, and we're going to do that for every single pair of twins. And that's the distribution that we're curious about. Okay, so we're not going to keep them separated anymore. We're going to put these distributions together by subtracting twin A minus twin B for IQ score. So we're going to call this the mean difference, and that notation is really crucial. I know you're looking at that going, that feels similar. It's a different idea, okay? So it's the average difference for each pair of twins is what we're looking at. So when we look at that full out distribution of finding the difference for each of our pairs, there's a difference of almost 6 IQ points. And now we're wondering, is that something of interest to us? So by the way, the standard deviation for that same distribution is 3.93. Proper method of analysis depends on how the data was produced, right? So if we have paired data, then we need to do some sort of a design like that. If that's how we, if that's how we created our experiment, because we were curious how that, biologically that set of twins is the same from birth, but then when you create different environments for them to grow up in, what happens? To analyze paired data, you start by computing the difference for each pair, and then you make a graph of this new distribution called the difference. And then you find your statistics off of that. And then you have fun. All right, so here's a more lighthearted example. It's not about children, being adopted and separated from their sibling. Does music help or hinder performance in math? Curious minds want to know. So student researchers Abigail, Carolyn, and Leah designed an experiment using 30 student volunteers to find out. So think about your experimental language. These were volunteers. We're going to randomly assign them, but our findings can only be applied to students just like these. Okay, keep that in mind. Each subject completed a 50-question single-digit arithmetic test with music and then also without music. So for each subject, they gave them two different tests and they changed the environment that they were testing in. So it's not like you're comparing student A to student B this time. You're comparing a student's first performance to a student's second performance. For each subject, the order of the music and no music treatments was randomly assigned. So there's your randomization. And the time to complete the test in seconds, what, I don't know, it says a second, so twice, was recorded for each treatment. Here's the data along with the difference. That was nice. They calculated the difference. And you see from the table here, they went with music minus without music. So that way we could see that difference similarly for all the student pairs. Well, I shouldn't say student pairs. They're their own pair. It's still a matched pairs design because remember, you can match yourself, like a before and after treatment kind of thing. Okay, so first things first, make a dot plot that represents the difference, music minus without, in time it took for the subject to take the test. So here's your dot plot, measuring the difference, and then they indicate what order. Okay, fascinating stuff, I know. Describe what the graph reveals about whether music helps or hinders. Well, there's some evidence that music actually hinders performance on the math tests. If you look carefully, 17 out of the 30 subjects, so a majority of them, actually took longer to complete. So when we add up all of these. So that is some evidence that actually the music was not helpful, which is probably what your knee-jerk reaction was, that you thought that music would help. Turns out no. Maybe. We'll see. Calculate the mean difference in the standard deviation. Well, that wouldn't be too hard to do in my calculator. I could enter all that data into list one and then do some one variable stats with it, because you know I'm not doing that by hand. So the sample mean, I'm sorry, the mean of the difference of the samples was 2.8 seconds when subtracted in that order. And then the standard deviation was 7.49 seconds. And then they want us to interpret the mean difference. So the mean difference is 2.8 seconds, which means the time it took these 30 students to complete the arithmetic quiz with music was 2.8 seconds longer on average than the time it took them to complete it without music, which means it slowed them down. Curious minds want to know why. There are two ways that a statistical study involving a single quantitative variable can yield paired data. So it could be that a researcher is recording two values of the variable for each individual. So the music example was one of those where we had a before and after situation, where we changed the environment for one person or treated them to something, before and after. And then the other option is you purposely pair subjects together. So the twins example was a good job of looking at that. And that was an observational study, not an experiment. I think I used the wrong language earlier, my bad. But that would be another version of pairing up your data. All of them were matched pairs designs of sorts, but these are the two examples that you're going to run into for this chapter. It is possible to carry out matched pairs experiments using method 2 if the researcher forms pairs of similar subjects and randomly assigns each treatment to one member of every pair. So the twins one was an observational study because we didn't we didn't force them to go live in poverty or, high income. That was just something we were coming in after the fact to look at data. However, you can still group up people, whether it be twins or similar people. I think we saw an example a long time ago about, how sunblock affects people, and we wanted to match them with someone who had similar skin tone to them. And then you randomly assign which person gets treatment A versus B. Okay, so if that's the case, if you're running an experiment, that's the part that's randomized. You don't randomly pair them, you purposefully pair them. You randomly assign them the treatment. All right, so surprise to no one, we got conditions, and they're the same conditions. So random data, random sample is how we pair the data. I said that weird. I think that randomization thing is confusing to kids, especially since I just babbled on this last screen. So here, if we think about what was random, when we look at that music math test thing, they randomly assigned how the treatments were applied to the person. So they randomly started you either with music or without. It wasn't purposely done, and it wasn't done the same to everybody. Now, in the twins example, that wasn't an experiment at all, but they commented down here that while you're purposely pairing the match set, you're going to randomly assign who gets what treatment. Okay, so there's the randomization in theory. I know on the observational study question, there wasn't any randomization happening there other than they randomly selected. Like they probably had a pool of applicants of, maybe we found 150 set of twins that fell into that category, and they randomly selected 12 of them. So there's a little randomization in there, I guess. We know from our work in chapter 4 that how we randomize those selections determines how then I can take my findings and extrapolate it out to a population. All right, 10%. Usually it's without replacement, so we got to follow the 10% condition. And then just like the last chapter, last part of this section, actually, normal and large sample has to be true. So the population distribution of the differences or the true distribution of differences in response to the treatment is normal. That would be great. Or else the number of differences in the sample is large, so something greater than or equal to 30. If the population has an unknown shape and we have a sample that's less than 30, then we have to go ahead and graph the sample differences to show that we don't have those extreme skews and outliers, just like before. So That formula looks awfully familiar, except you'll notice the notation. They do X bar sub diff to represent, a matched paired data set. All right, degrees of freedom. Just like you would think, it's, diff minus one, n sub diff minus one. And then, of course, we're going to be able to use technology and get an even better picture of a confidence interval in those cases. Oh my gosh, I would love to be a twin and dress like my twin all the time. These guys got it together. All right, the data from the random sample of identical twins is shown again. Now we're going to construct and interpret a 95% confidence interval for the true mean difference in IQ scores. So, 4-step. Starting with state, we are going to conduct a 95% confidence interval for the mean difference, where the mean difference is the true mean difference of high income minus low income in IQ scores for pairs of identical twins raised in separate households. Watch your context on these because you got to be real explicit. When in doubt, write it out. For real. All right, it's the plan stage. We now have now careful guys, I know it's 2 samples originally, but we paired them. So it's actually a 1 sample. So you have a 1 sample T interval for the mean difference. So random sample of 12 pairs of twins. One raised in high income household and the other raised in a low income household. Okay, so there's the randomization aspect. 12, I'm sure it is less than 10% of all pairs of identical twins raised in separate households. That's a really sad thought, but I think there's a lot of twins out there who do get separated. And then we got to check the fact, do we have a large enough sample or is it normal by default? Normal-ish by default. And when we look at, and what we're looking at here, guys, is the difference in the match, right? So we look at each twin pair and we plotted their differences. Well, we didn't have enough of a sample. We weren't bigger than 30 or bigger, 30 or bigger. But when I look at this dot plot, I don't see anything crazy happening. I don't see a lot of skew or outliers, so we're good to go. Now, only crazy people would use the formula. No, that's not true. This one's not too bad. So you could use technology, yes. You still would have to tell me your X bar, your S, and your N, and then use the proper notation here, X bar sub diff, S sub diff, and N sub diff. Your degrees of freedom is going to be 11 because, there's 12 pairs of twins, so 11 is your degrees of freedom. They calculated the critical value T star using table B, it looks like, and then they cranked away in the formula. Now remember, guys, this is a 1 sample T interval. This is a very easy to confuse question, and I think the fact that both of these topics are in the same lesson is kind of scary for me as a teacher. So we really have to kind of hit home how these are different problems that we talked about in this lesson. At the beginning of the lesson, it was all about, um, subtracting the 2 distributions, and then here it's pooling, I shouldn't say that, pairing the data together and creating a single distribution that's measuring the difference of all of those pairs. Not sure if I made that better or worse. All right, so there was your confidence interval. So we are 95% confident that the interval from 3.336 to 8.330 captures the true mean difference, in that order, in IQ scores among pairs of identical twins raised in separate households. Fascinating. All right, so this is something for you to try on your own. We're going back to the students who, remember, were taking a math test, and they had to take 2 different math tests, one where they played music and one where they did not. The students were randomly assigned to take one first versus the other, and they want us to construct and interpret a 90% confidence interval and then talk about, what does that mean? So pause the video, try these on your own. You got answers coming your way in 3, 2, 1. Here you go. All right, so state 90% confidence interval for mean difference, which is the true mean difference in music minus without, in time for students like the ones in this study to complete the arithmetic test. It's important that they say like ones in this study because remember, these were volunteers. All right, they're going to plan it out because we're kind of match pairing them. This becomes it's yourself beginning and after. This is a 1 sample T interval for the mean difference. These were volunteers, but they were randomly assigned whether they got music or no music first. So there's the randomization of it. And then 30 is definitely greater than or equal to 30. So check, check, check. The do step. It's up to you how you do it. Um, you can use the formula. You could use technology. You just have to make sure that if you're using technology, you state that you used a one sample T interval and give the interval itself from technology, and then also state the degrees of freedom, which happen to be the same degrees of freedom from up above because it was just 30 minus 1. And then we're going to conclude. So 90% confident that the interval given captures the true mean difference, music minus not music, in time for students to complete the arithmetic test. Now the follow-up question asked about what does the interval suggest about whether music helps or hinders? So that interval is all on the positive side of 0, right? So that indicates taking the test with music would take longer according to this interval. So having music seems to slow them down according to this interval on average. So I, as a math teacher, might argue that that doesn't necessarily mean that they are doing less well on the test. Maybe that's something else they can expand and look at in this little experiment of theirs. So not just necessarily how long it took you to take the test, but how did this affect your accuracy? Because who knows? Maybe they took longer, but they were more accurate. Things to think about. And that's it. So that's all chapter 10 was. It was a whole bunch of confidence interval work with means. I think the trickiest thing in this chapter is focusing on, what when you have the two samples, what are we doing with these two samples? Are we trying to match the data together like we did with the twins problems and with the music problem, or are we keeping the data separate from these two samples and end up subtracting the distributions themselves at the end? Because that's a different question. In fact, it's a different set of keystrokes on your calculator if you want to be fair about it. So we'll practice that a lot. We'll probably screw it up a lot too, but that's part of learning, isn't it? All right, thanks everybody. Chapter 11 is next, and we're going to finish up with tests with means, I believe. We're going to start getting into chi-square and all sorts of good stuff, and we are almost done. Oh my goodness, I can't believe it.